Hi, this is Aves from RIS. We are on chapter number 5. We had previously completed the requisite topics for Federal Board reduced syllabus along with 2 examples which are included in the syllabus. Right now I'm going to solve in a quick manner all the numerical problems for this chapter which are included in the Federal Board reduced syllabus. So let's start. We're starting from 5.1, which states that find the gravitational force of attraction between two spheres, each of 1,000 kilogram mass. The distance between the centers of the spheres is 0.5. It is a similar one, just like example 5.1, except the data is a little bit different. So let's write data. As the data, we have M1, which is 1,000 kilograms, M2, which is also 1,000 kilograms. The separation between them R is 0.5 meters. We do know the value of G, which is 6.67 into 10 to the power minus 11 Newton meter square per kilogram square, right? We want to calculate the force of attraction, right? So let's get to solution. F is equal to G M1 M2 over R squared. 6.67 into 10 to the power minus 11 into 1000 multiplied by 1000 divided by 0.5 whole square. So the force is going to be very simple, 6.67 minus 11 multiplied by masses divided by 0.5 squared. So it's turning out to be 2.668 into 10 to the power minus 4. Now if you remember from the example, this is Newtons, that the value was quite smaller as compared to the value we had before. It was somewhere around I guess 6.67. It was 6.67 into 10 to the power minus 5 newtons. Now this is 10 times, this is 10 times stronger as compared to this one. And why? We had simply moved the spheres, which were like before 1 meter apart from each other, right, to a point where they're just 0.5 meters apart. The masses are the same. If you go through the data, you'll understand both in the example 5.1 as well as the numerical 5.1, the masses that we have taken are the same. That's 1,000 kilograms for each mass, but the separation between them has been reduced. So by reducing the separation between masses by half, I've got a much bigger value for this, right? This is numerical problem 5.1. Now let's get to 5.2. The gravitational force between two identical lead spheres kept at 1 meter apart is this, right? They have given us the force. We have force, which is 0. How many zeros? 0, 0, 66736 newtons, if I'm not wrong. Yes. And R is 1 meter. Now this is very interesting. Find their masses. Now remember, they're saying two identical masses. This is also M, this is also M. They are separated at a distance of 1 meter, right? And the force that is between them is already given to us, right? We don't know what this is data, what the masses are. We don't know M1 is equal to M2 is equal to M is equal to unknown. We don't know these masses. I'm going to write them as M1 as M2, which are being equal. So if I calculate either of the one, I can calculate the other two. So I've let them equal to a symbol formula as m. So if I write the Newton's law of gravitation again, F is equal to G m over r squared, and you can simply take a square of these as well. Doesn't really matter. Let's convert force into a more appropriate notation. 6.67 into 10 to the power, let's say 1, 2, 3, minus 3 newtons, right? So this is 6.673 into 10 to the power minus 3 is equal to 6.67 into 10 to the power minus 11. We have squared these masses because these are equal as per the question, and we're going to have a square of 1. It eventually is going to be 1. So if we just simply have to move this downstairs, right? 6.673 into 10 to the power minus 3 over 6.673. This is also actually 6.673 if you go into more significant figures with this. This is going to m squared, right? This whole thing gets cut with this, so 10 to the power minus 3 plus 11. This is since this is a denominator, this is going to go up and get added, so this is going to 10 to the power minus 3 plus 11 is equal to m squared, right? Now I'm going to use this tiny little portion to solve this. So m squared is equal to 10 to the power 8, right? But we are having square over here, so we're going to take the square root on both sides, 10 to the power 8 square root. So let's solve this on a calculator. We're taking square root of 10 to the power 8. So it turns out to be 10,000 kilograms. That is about 1 ton, and that is again for each mass. So m1 is going to be 10,000 kilograms and m2 is going to be also 10,000 kilograms, as we know that both masses are equal and they're equal to m. We have calculated m, so we have calculated both our masses. So this is numerical problem 5.2. Moving on to the next one. Now we have numerical problem 5.3, which states find the acceleration due to gravity on the surface of the Mars. Mars is a planet which has a different mass and different acceleration. So let's get down to it. This is 5.3. We are trying to note down the data. Now we have the mass of mass of Mars. I'm writing small m for Mars, right? And which is 6.42 into 10 to the power 23 kilograms, a little lighter, 10 times lighter than you can say Earth in that regard. And the radius is even smaller. Radius of Mars is 3370 kilometers, which is 3.37 into 10 to the power 6 meters, right? So we want to find the acceleration due to gravity. We don't know g on Mars. Solution: if you refer to topic 5.2, we had discovered that this is also possible, where since that was from Earth, we're going to calculate it for Mars. We're going to put small m's all around. So we're going to get gm, gravitational acceleration of Mars would be 6.67. It does not change for any object in the universe. It remains the same, the capital G. Mass of Mars 6.42 into 10 to the power 23 divided by 3.37 into 10 to the power 6. And this is going to be squared, right? Now gm is going to be about 3.77 meter per second square. Once you will solve this using calculator, this is the value we're going to get. So this is the value for the gravitational acceleration on Mars, right? Which is nearly 3 times less than Earth. So I'm going to weigh 3 times less than that. What's my weight on Earth? It's going to be 3 times less on Mars. So moving on to the next numerical. Five and 4, which states the acceleration due to gravity on the surface on Moon is 1.62 meter per second square. The radius of the Moon is 1740 kilometers. Find the mass of Moon. So 5.4. Now this is regarding Moon. So let's write the data. We do know that G on Moon, now this is the small m is for Moon, not for Mars, is 1.62 meter per second square. The radius of the Moon, again R for Moon, not for Mars, is 1740 kilometers, which is 1.74 into 10 to the power 6 meters, right? And we want to calculate the mass of Moon. We know the value of G, so let's get down to solution. Similar as we're going to use the same equation as of the previous numerical. This is going to be Rm whole squared, right? Now we want to calculate this instead, right? To calculate this, let's keep on one side and move rest of the pieces out. So this goes up, this goes down, so we're going to get Grm squared over capital C, which is going to be Gm is equal to 1.62 into 1.74 into 10 to the power 6 whole squared divided by 6.67 into 10 to the power minus 11. Now most of you when they're taking square on calculators with the exponent of 10, most of you do mistakes with the syntax of the calculator. Please mind that. You can watch a YouTube video on any calculator model that you're using on how to use that calculator without such errors. Most of the people take the square, and the square actually gets on top of just this and not the whole value, or at times on this and not on the 10 power 6, so they get a wrong value, and hence they lose the marks of the numerical. So keep that in mind. If you're having difficulty with the use of calculator, you can always search on YouTube with the calculator model number, and you'll get all the tutorials how to use it, how to take power, 10 power, and how to solve 10 power squares, right? It's very easily available on the internet. So the value of the mass of Moon is going to be 7.35 into 10 to the power 22 kilograms. It is about 100 times lesser than that of Earth. Not 100 kilograms, but 100 times. That means 2 less zeros as compared to the mass of the Earth. So this is 5.4. We're coming to our last numerical for this chapter. I hope we have covered this chapter and we have done all that we could in understanding this chapter. If you still have any issues, you may share those with me. This is 5.5. The last numerical for the reduced syllabus. Let's write the data along with the statement. Calculate the value of G. We want to calculate the value of G at a height of 3600 kilometers. We are going to convert this into 3.6 into 10 to the power 6 meters, right? K, I'm resolving kilo as well as the 3 zeros over here. So we're going to get 10 to the power 6 because meter is the standard unit for length in SI. We are going to above the surface of Earth. So we're talking about an object which is above the surface of Earth. So the radius of Earth is going to be there, 10 to the power 6, which we are going to add to this. This is nearly as much distance as that of Earth. This value does not really affect. However, this really affects. So you can see these are in the same power, so it is going to be added easily, and it would be quite the distance. This is so we can say this is nearly as far as the radius of the earth. The object is nearly as far as the radius of the earth, right? So let's get down to solution. Again, we're going to use the same equation, mass of earth. In this case, since we're using we're not taking it to part, it's the mass is bigger, mass of the earth is bigger, so that is the more dominant force that is going to be there. Re plus h is what we're going to have at the bottom to compensate the height. So small g is going to be 6.67 into 10 to the power minus 11. Mass of the earth 6 into 10 to the power 24 divided by 6.4 into 10 to the power 6 plus 3.6 into 10 to the power 6, which is going to be about 10. So this is nearly going to be about 4.0 meter per second square. So this is the available acceleration of gravity at a height of this much meters, right? So if you go that much high and if you start moving towards, if you stop and then let the earth pull you towards itself, so the earth is going to start pulling you with an acceleration of 4 meter per second. Now that is the end of all the numericals. I hope I was able to give you the insight about this chapter, and I was able to give you a brief explanation of the chapter and all the topics and the basic information about this chapter. Please go through the context and read all the important topics that we had covered, and let me know if you have any questions, anything that you want to understand, any numerically you want me to revise. Otherwise, these videos are going to be available for you as long as Teams is available, and you can review, you can revisit these videos as many times as you wish. So this is all for chapter number 5. I hope we are on the same pace now. We're going to be at the same pace with chapter number 6, and you won't be feeling lagged up with chapter number 5. Thank you.